All right, welcome everybody to this Mado lecture. And it's my honor and pleasure to introduce to you Professor Jilt Sietsma from Delft University of Technology. And he will present about quantifying dislocation structures simply from tensile tests.
Okay, thank you, Erik. Before I start, let me just say that if you have questions, just interrupt me. And I cannot see you all, I might not see the chat, so just to speak out if you have a question in between. That might make it an even more lively discussion. So I'm going to talk about dislocations. Dislocations, in my view, are one of the most poorly known aspects, phenomena in metals in relevance to their importance, because they determine the behavior of metals to a great extent, but still we know fairly little about it. They're extremely complicated. I just drew up this picture of dislocations in the transmission of electron microscopy picture. And I tried to quantify dislocations in a bit more extent than we used to, using tensile tests. So no difficult techniques, just standard tensile tests. And I'm not talking about the Taylor equation, as you will see. Well, you all know what a dislocation is. Do you see the dislocation here? This is a closely packed plane, and you see that something's wrong here in the middle. Hopefully you see my mouse. And if you look at the character of the dislocation, these are crystallographic planes. They're perfect planes. And if you look in between these two lines, you see 7 planes on the bottom side and 6 planes on the top side of the dislocation. So that is what we call an edge dislocation with an extra half plane on the bottom side in this case. They occur at random. They are present in every metallic crystal. You cannot avoid them. The way to quantify them, to characterize them, is by a so-called Burgers circuit. So you take a starting point, you go in this case 9 positions up, 8 or 9 to the right, 9 down, 9 to the left again. And if there's a dislocation in between, as is the case here, you're left with a vector between your starting point and your end point, and that's what we call the Burgers vector. We all know this concept, I guess. Here you see it again in the model that we have in our laboratory, a model that was made at the time of Professor Burgers, because Willy Burgers was a professor in our department who invented or defined the Burgers vector at the time. Dislocations were known already. The time is before the war in the 30s. Dislocations were known already, but it was still a question how to characterize them. And then Professor Burgers and his brother, who was a hydrodynamicist, very good in mathematics. Actually, his brother thought of the idea, and that's why Professor Burgers always called himself the uncle of the Burgers vector, and not the father of the Burgers vector. That was his brother. Well, dislocations are very important for the mechanical behavior, the strength of material, the ductility of material. And we know that during plastic deformation, we have so-called Frank Reed sources. So this is a typical picture. You have a dislocation segment here, initially the red segment, it's straight between 2 pinning points. Pinning points might be other dislocations, might be precipitates, might be solid atoms. And when you apply a stress, the dislocation wants to move, but it's pinned in A and B, so it bows out into a semicircle. And if you even further increase the stress, this circle bows out further, and in the end, when these 2 parts meet here, they annihilate, and you're left with the yellow one, the big circle around the source, and again the same segment, which can therefore do the same thing again. This whole behavior is related to the so-called dislocation line stress, and that's the fact that the dislocation itself tries to oppose the applied stress, because when it's bowing out from this red state, it gets longer, and getting longer means a higher defect energy, and therefore you get a stress to push it back to go to lower energy again. That stress is inversely proportional to the curvature, the radius of curvature of the bowing out, and that's therefore reaches a maximum when the radius becomes minimal, and that's in the semicircle. So when this 2r equals L, so the length of the segment. That's the highest possible dislocation line stress. And when you apply a stress beyond that, above that value, then you get yielding. So that's at the level of a dislocation, this critical stress in which the Frank read source reaches a semicircle is the point at yielding, the point at which yielding starts. Well, this concept is well known. This is a theoretical picture, but it's also shown with molecular dynamics. You see dislocation in molecular dynamics showing this behavior of a Frank read source. And you can also sometimes see it experimentally, as you can see here in the transmission electron microscope. There you see the Frank read source, and it annihilates and it starts all over again. So this is all well known, I guess. Often when we look at dislocations, the only way we can really see them is in a transmission electron microscope, and then it often looks like this. There are separate dislocations. Here you see different dislocation lines, separate entities, but theoretically a dislocation cannot end within a crystal. And that was already recognized in the beginning. Cottrell is a very well-known name, of course. His work of 1975, no, 57. And he said it's a network. And indeed, it's a network within a crystal because a dislocation cannot end. So what do we see here in transmission electron microscopy? We see separate dislocations because the thickness of the sample is smaller than the sizes in the network. So this is a typical TEM sample, which shows that the structure that you see in TEM, it helps to see the dislocations, to see the move, etc. But it does not represent the real dislocation structure in the material, because the real dislocation structure is the 3D network of interconnected dislocations. So you can never say a dislocation moves or it doesn't move. It's the whole network. So it looks rather something like this. This is in strontium titanate. So it's a sort of ceramic material, but it also displays dislocation. And this is what it looks like here in reality. So when I use the word dislocate, sorry, yeah? No. So when I speak about the dislocation structure, I mean this three-dimensional network, and that consists of connected segments, because they're all connected. There are pinning points. The pinning points might be dislocations, might be precipitate, might be solid atoms, as I said. But in between those pinning points, we have dislocation segments. And of course, there will be a distribution of segment lengths. They will not all be the same. Now, when we want to quantify the dislocation structure, in fact, we only use one property, the dislocation density. And that can, dependent on the condition of the sample, be roughly between 10 to the 10th and 10 to the 15th per square meter per cubic meter. Sometimes dislocation cell size is another quantification. But you can imagine, and that's why I say we by far do not understand enough of dislocations. This complicated network, experimentally, it's already a problem to determine the dislocation density. Only one number to characterize this 3D network of dislocations. So that's the experimental, the theoretical concepts are fairly clear. The experimental evidence is very limited. There are basically three techniques that are being used to quantify the dislocation density. The broadening of dislocation of X-ray diffraction peaks, TEM, and EBSD. Well, they all have their disadvantages. In X-ray diffraction, it's quite a complicated theory behind it with a lot of assumptions that make it difficult to judge how, what the consequences are of all those assumptions. TEM, as I showed before, has serious drawbacks in the sample preparation. In the first place, because it's very thin. So you have a lot of surface, so dislocations can also escape to the surface. So, and you don't know exactly how thick the sample is. So quantifying dislocation densities from TEM is also rather difficult. And EBSD, in EBSD you can measure the local crystallographic orientation, and gradients in that orientation can be linked to what's called geometrically necessary dislocations. So not all dislocations. And also there you look very local, of course, in a 2D representation. So these are ways to quantify the dislocation density. but there's a lot more to it than just these numbers, I think. Another way in which, and then we come closer to the tensile curve. Tensile curves are sometimes linked to dislocation density. It's the so-called Taylor equation, this equation here, which is well accepted and it's been shown to be quite reasonable very often. But then you have to choose a few parameters. So if you know the dislocation density, you can link it to the flow stress, so the stress needed to plastically deform the material. But you need to know what this sigma zero is. You need to know what the alpha factor is, the parameter here. So the alpha is a parameter of this equation. M is the Taylor factor, translating shear to tensile stresses and strains. G is the shear modulus, and B is the length of the Burgers factor. So that's a certain relation in which the role of dislocation in strain hardening is expressed. Another way to look at strain hardening, and that will be part of our analysis, is so-called Koch-Megging plot. Koch-Megging plot is a plot out of the tensile curve, the derivative of the tensile curve, the sigma the epsilon, as a function of the applied stress, and then the applied stress above the yield stress. So the stress here, sigma W in this case, is the applied stress minus the yield stress. Why do we do this? We do this because dislocation theory gives this expression for the change of the dislocation density with strain, and it has one production term and one annihilation term. And if you combine this with the Taylor equation in the previous slide, then you get this equation here, and that is a straight line of the derivative as a function of sigma W. And we like to have straight lines, so this is an analysis that's often used to determine these parameters U and omega to quantify the dislocation behavior. But, so these are things that apply to the plastic part of the tensile curve. And we're going to look at the pre-yield part of the tensile curve, so before the yield stress. In textbooks, you always find a plot like this, with a straight line, with a slope is the Young's modulus, and at a certain point you get yielding, then you get strain hardening, necking, and fracture. We all know that, of course. The point is, so we're going to look at this pre-yield part, very low stresses, low strains. The point is that this part is not straight at all. On the right-hand side, you see a real measurement, austenited at 900 degrees, and you see that the dotted line is the theoretical Young's modulus line, the Hooke's law, but already at very low stresses. There's a deviation, so there's an extra strain. There are two components of the total strain, the elastic strain, and with elastic I mean elastic due to the elasticity of the lattice, and an anelastic strain. And that anelastic strain increases with increasing stress and strain, and that's the interesting part we want to look at. Well, this is well known. Part of the problems, there's never been a full explanation quantitatively, but qualitatively it was known that it's due to dislocations. And one indication, for instance, is if you take something like the average slope here, of course, if you don't magnify it so much, you can take an average slope up to the yield stress, for instance, and you do that after plastic deformation, you see something like this, that the average slope decreases with increasing plastic strain. So before you make a plastic strain, then you do a tensile test, and you see the more plastic strain, so a higher the dislocation density, the lower this apparent Young's modulus. So this is a fairly direct indication that this apparent Young's modulus being lower than the real Young's modulus is due to the fact that there are dislocations in the material. Question is, of course, how? So that's the link you can make from this. This anelastic strain must be linked to dislocation somehow. So what happens? Then we look at the segments. We come back to the segments. As I said, the 3D dislocation network, the dislocation structure, consists of segments between pinning points. We made this schematic picture here. And what is indicated here, if this part is LD length segment is pinned between these 2 points. When you apply a stress, it starts bowing out and it covers a certain area A. How does it work? At low stress, so at stress 0, the dislocation segment will be straight because that's the condition of lowest energy, defect energy. When you apply a stress, you have 2 stresses. One is the applied stress on the dislocation, which makes it move upwards in this case. And the other is the line stress of the dislocation, which wants to make it go back to the equilibrium position, wants to decrease its defect energy. And if the stress is low, you can still have equilibrium between the 2. So if you apply a small stress, the dislocation will start bowing out, not plastically, it will not become a frayed reed source yet, but it will bow out a little bit up to the point where the line stress is equal to the applied stress. And then you have a balance and it stops. Then, before you come to that point, is it already covered an area A, and you probably know the strain, in this case the anelastic strain due to the dislocations, is proportional to this area A. Then we have the Taylor factor, we have the Burgers factor, and we have the number of these segments per unit of volume. And if you realize that the dislocation density is equal to the number of segments times their length, then you see that this anelastic strain is proportional to the dislocation density and is inversely proportional to the length L. And so this is the concept, and that's the idea that we had to, because the anelastic strain, so the deviation from Hooke's law, from the Young's modulus, is due to dislocations, and it's a way to quantify that. Of course, it continues when the applied stress becomes bigger, the anelastic strains become bigger, and that's exactly what you see in the tensile curve. That we studied in the Cox-Macklin plot, because here you see the Cox-Macklin plot again, the one that I showed before. This point here, SW equal to 0, is not zero stress, but it's the yield stress, because we subtracted the yield stress. And you see here before something is already happening. So if we make this plot not from the yield stress and higher, but for the full range of stresses, and it's really this curve. If you determine the derivative, you plot it as a function of stress, not from the yield stress, but from really stress 0, you get a curve like this. Now, without dislocations, the starting point, or before the yield stress, you would have the Young's modulus, so it would be constant here in the derivative. But there's clearly a consistent decrease of that part, and there's information on dislocations there. So by looking at this extended Cox-Macklin plot, as we call it, because the actual, or the classical Cox-Macklin plot is only this part here, we look at an extended Cox-Macklin plot, including the pre-yield part, which contains information on dislocations. Before getting to the dislocations, it's also clear from this plot that there is a distinct transition from this pre-yield behavior to the plastic behavior. So instead of the 0.0% offset, which is the definition of the yield stress normally, here you see a very clear point, clearly identifiable point, in which the reversible pre-yield behavior transits to plastic behavior. And that is a sort of physical concept and not determined by 0.2% or by 0.1%, but really a point at which the behavior of the metal changes from pre-yield to plastic deformation. And it can be identified in this extended Cox-Macklin plot. And you see it also here in this curve. They have the same behavior here. They just didn't pay attention to it. Well, it can all be quantified, because if you assume this bowing out to be a circle segment, you can just do the mathematics. You end up with a function that's a bit complicated, but can be handled, of course. So this function, this pre-yield slope, theta was d sigma d epsilon, is proportional to the yield, to the Young's modulus. the Poisson ratio, these two parameters of the dislocation structure, and this function f of s, and s is the reduced stress, so sigma over sigma yield, so it's between 0 and 1. And sigma yield, that's the dislocation theory, as I mentioned before, is GB over L. So if you plug in this f in this equation, you get a larger equation, but in the end, it contains two fitting parameters, the dislocation density and the segment length. And that's, of course, something like an average or effective segment length, because there will be a range of lengths. So we applied it to this measurement that I showed before, and we get a very good fit with this equation with very reasonable values also. Not only enough to have a good fit, the values should also be of physical relevance, of course. So dislocation density of 9 times 10 to the 11 per square meter and an average segment length of 400 nanometer seem quite reasonable values. And you see the fit is very, very good. As I said, from this transition point, that is the real yielding point, the real transition from pre-yield behavior to plastic behavior. Here you have the 0.2 offset sigma yield stress, and here in the tensile curve you have the yield stress that is related to this point here. You don't see it in this curve, but you do see it in the derivative. And sometimes we found the sigma yield to be above the 0.2% value, sometimes below. So it's not a fixed law that it's higher or lower. Well, we apply this in a number of cases, and I'll show you some examples. Here we have two iron alloys, pure iron, and a low alloy steel. You see here 0.8% carbon, a bit of manganese, a bit of silicon. And we apply this extended Cox-Magging plot. That's what you see here. This, the derivatives, the sigma, the epsilon, as a function of sigma. And you see the same type of behavior as before. It starts below the Young's modulus. This solid line is the Young's modulus. And it bows off. And we did it without prior plastic deformation and after 14% of plastic deformation. We did 3 measurements. And you see that all 3 measurements can be fitted with a single curve, and that gives values of 2 times 10 to the 13th per square meter dislocation density, 233 nanometers segment length, and after 14% plastic deformation, the dislocation density is increased by a factor of 5, and the segment lengths have become smaller due to the pinning of other dislocations. Same thing for a low alloy steel. Without prior plastic deformation, you get these numbers. In this case, with a plastic deformation of 15%, you get a more than 10 times, well, actually 20 times increase of the dislocation density and more or less half the line length. We compared it with X-ray diffraction for the two deformed materials. And you see that they're more or less the same. The squares are of X-ray diffraction, and the circles are with this method. So, of course, L we cannot check with X-ray, but these are fairly reasonable numbers.
May I ask a question, Jilt?
Yeah, sure.
So how do you explain that the dislocation density for the steel with 0 plastic deformation is smaller than for pure iron?
Well, all materials have had a previous treatment. So maybe I should call it as received instead of...
Okay.
Because the state in which we get it, we did not do anything. So we did not apply next plastic deformation. But of course, it's another material, and we don't know exactly what the last step or steps were in the treatment of the material. Right. This comparison with X-ray, a lot of reviewers asked for it. I never know what to think of it. X-ray diffraction is also not very accurate. So if we get the same as X-ray, of course, it's encouraging. If it's different from the X-ray values, like for the pure iron, is our value better or is the X-ray value better? I don't know. X-ray is more widely accepted. That's certainly the case. So we did this And that's one thing I have to say. These are very careful experiments with 2 extensometers, and that's because in general, a tensile test has been optimized, or machinery has been optimized to study the plastic behavior. And we want to study the elastic pre-yield behavior, the elastic and inelastic behavior. So very small strains, so we have to be very careful with straight samples, perfect alignment, etc., because those are things that are not so important when you study plastic deformation, but are very important, of course, if you study the very small scale of the pre-yield behavior. So we did a couple of tests in which we did cyclic loading. So what we did, you see it, took 2 steels, an IF steel and a low alloy steel. So we applied a plastic strain of 0.5%, then unloaded down to 10 megapascal, and then reloaded. And we did that 20 times. So in every step, we have a loading curve that has its pre-yield behavior. So after every unloading, we load again. After unloading, all dislocations are in their straight condition again. Then you start loading again, and they start bowing out before yielding once more. And from that part, so we have 20 pre-yield curves here, and in each of them we can analyze the dislocation behavior. Yes, so what you see on the right-hand side is again this extended Koch-Making plot. The slope is below the Young's modulus for 3 cycles, cycle 3, 10, and 17. So that's cycle 3, this is for the IF steels, and the blue ones is this one over here. Cycle 10 is somewhere over here, and cycle 17 is somewhere over here. So those 3 loading curves, we took the derivative, we made an extended Koch-Making plot, we plotted, we fitted the equation that I showed before, and we get this type of values, again, realistic values for the dislocation structure parameters. And you can do that for 20 steps. So these are all 20 loading cycles that we took. We skipped for the low alloy part the yield flag, because that's a complication which we think would be too complicated to take along. So we started a little bit later here. But you see a very consistent increase in the dislocation density and a very consistent decrease in the segment length. This also makes it very well possible to test the Taylor equation. And you see dislocation density here and the yield stress. These lines are the fits. So you see it's a perfectly square root behavior. And we have for both practically the same value of this alpha parameter, which is the only fitting parameter. And what you see here is the relation to the actual meaning of the alpha parameter, because this is the classical Taylor relation, and this is the equation for the yielding of dislocations. And if you combine them, you see that the alpha parameter is equal to 1 over L squared root rho. It's not an arbitrary parameter, it's the parameter that is governed by the dislocation structure in the sense of these 2 parameters. So when we determine alpha from the fits, we can determine rho L squared, which has a value that is below the picture where I see you, 6.4. And I find it very remarkable that this good fit means, and the validity of the Taylor equation means, that this alpha parameter, so the combination of segment length and dislocation density, is constant over the whole curve. So whereas you increase the dislocation density by a factor of 10 roughly, even more in one case, I think, somehow the structure is consistent in the sense that the segment length scales with the square root of the dislocation density. I don't know why. I find it very intriguing.
You
also, Yuri?
Yeah, thank you. So could you please come back one slide with, this rho L square is constant, seems to be for these 2 type of steels. Did you check it for other type of steels or material? Is it constant value as well and in which range it varies? It tend to vary.
It ranges roughly between 5 and 15 or so.
5 and 15.
But I'll show an example later in which it's not constant.
Ah, yeah, okay.
And that would mean
L
that
is the cell size here, you mean, or L stands for what?
now this is not a cell size. It's a segment length, L.
Segments length, okay.
And of course, if you have cells, that will very strongly influence, and that's something we didn't study yet, but that would very strongly influence the distribution of segment length, I think.
But also it will depends on the geometry of the cell, because
Depends on the way the cell walls are built up, because the density will be much higher in the walls, so the segment length will be smaller there than in the interior. So the overall dislocation density will be low. Well, low because you have dislocation poor regions, but where there are dislocations, the segment lengths will be relatively small, I think. Something like that.
yeah, okay, yeah, thank you.
I'll show an example of martensitic steel later in which we don't find a constant rho L squared, but many people confirm this Taylor equation with always the question, of course, how accurately can you, or how convincingly can you verify this equation if you don't have a very good method to measure rho?
Yeah. Yeah, normally what people do, they work with constant alpha. In fact, but alpha itself, what we have seen as well in our simulations, it depends on the dislocation density, and it's logical because if you look at the base, actually the theory behind the alpha, it related to the dislocation course, and with increasing the strain, you produce more dislocations there. So alpha should be dependent on this, because all the time you change the configuration of cells, of the amount of dislocations. So
Yeah, but the Taylor equation, if the Taylor equation is valid, then alpha is constant.
Yeah, because then you have alpha square root of rho. You have to treat it as entity. Yeah.
Very intriguing. We also applied it to a dual phase steel, and there also we find reasonably good fits and also validity of the Taylor equation. And that's one step further, because the difference, of course, is a dual phase steel has two phases, martensite and ferrite. So the other two were one phase materials, so you can say there's one dislocation density. So if you take one average L value, then it will sort of be okay. In this case, dual phase, the dislocation density in martensite will be a lot higher than in ferrite. And so you have a sort of bimodal segment length distribution, dislocation density distribution, but still it works fairly well with a single value for L, an average value for both phases at the same time or so. We applied it to a martensitic stainless steel, and here you see we did 5 loops here, again with 0.5% strain in between, but of course the martensitic steel has a ductility that's a lot less than the other steels. And here we looked even a bit more precisely. What you see in this curve here is again the extended Cox-Mackey plot, so theta, d sigma d epsilon, as a function of the applied stress. That's the blue curve, and you see a transition here to yielding behavior. But we also determined the derivative of that curve, so that's the red curve. And that shows an inflection point here. A minimum in the derivative means that there is an inflection point here. And the theory of the equation that I showed for the pre-yield behavior, so the reversible dislocation behavior, does not have this inflection point. So what we say is the inflection point is the point at which the behavior of the material significantly starts to deviate from the pre-yield behavior, from the reversible dislocation behavior. So that's the point where yielding starts. And yielding starting means yielding of the longest segments, because they have the lowest resistance to yielding. And here at point C, more or less, it becomes constant. So that's where you enter into the real plastic behavior. That's also coinciding with this point. So we think that this region B In A, we have reversible pre-yield behavior. In B, we have a transition region in which both behavior apply. The longer segments will already plastically deform. The smaller segments will still deform only reversibly. And then in C, we go to irreversible plastical behavior. So that means this value here, sigma yield S, I don't remember what the S is for, but anyway, that's related to the longest segments, and this sigma yield is related to the smaller segments. So in this case, we can determine the dislocation density for these 5 points.
Hi, Jilt. May I ask a question back to the previous sheet?
Yeah.
And the ladder curve is the derivative of the strength. So if you apply this to here, it became string dependent, or it's
Sorry?
is this, so this can be cancelled, this value after this deviation,
I
this
cannot
can
see
be cancelled.
what you mean by this can be cancelled. We
Yeah,
have
so
the blue curve is theta, the
you
sigma, the
apply
epsilon.
this to here. Can this be cancelled? Then you get only string
I cannot
dependent.
see what you mean by this, Lee. I cannot see your mind.
Oh, you cannot see. Okay, sorry. I mean the item of the theta. If you apply this to here, then can we this cancel this?
We cancel the sigma.
Yeah.
No,
maybe I'm wrong.
It's a derivative, so it's d squared sigma, d sigma, d epsilon.
Oh yeah. Okay, you have one
So
more.
the first
d,
derivative is respect to
Yeah.
epsilon, and the
Yeah.
second is just the slope of this blue line, and then you get the red line.
Okay.
If you would do
So
that
it's-
for the theoretical equation that I showed before, so if we would take the derivative of the theoretical equation, the red line would be continuously decreasing, but it shows a minimum, so that's an inflection point here, and that's where we say it starts significantly deviating from the reversible pre-yield behavior.
Okay. Yeah. Thank you. Yeah.
So by looking at these points here as well, we can determine on the left-hand side, the low stress side, the longest segments, and on the high stress side, the smallest segments. So we have an L max and an L min. Dislocation density increases as a function of strain. The segment length decreases, and you see that the distance between these 2 points is something like indication of the width of the segment length distribution. And with increasing plastic behavior, that width becomes smaller and smaller. This is the case in which the rho L squared is not constant, it decreases. So in this case, the Taylor equation did not apply. So red is the maximum length, if I remember well. So it increases the dislocation structure factor, rho L squared increases with increasing strain. Well, if we load and unload, I look at the loading part now, and that is gives rise to quantifying these parameters for the dislocation structure. Also, you have an unloading part, of course. And if we magnify the unloading part and we subtract the lattice elasticity, so we subtract Hooke's law, we always get something like this. From the point of unloading, it first continues a bit. So strain still increases, and then it starts to decrease, and then we get the loading curve again. And you see that this hysteresis loop is very strongly dependent again on the dislocation density. The higher the dislocation density, because these are the 4 loops. So loop number 4 is at the highest plastic strain, so the highest dislocation density. So you get a lot of deviation from Hooke's law, actually. Well, a few things. One is, in the beginning, when you start unloading, the strain still increases, but not right away decrease. And that we can understand from the Frank-Reed rings around the Frank-Reed source. They don't go back because they have a very low dislocation line strength. So they continue a bit, and that gives the extra strain. We would like to, so we have an equation for this loading part, And we would like to have an equation for this unloading part, also because it's very important for springback. You're probably aware of what springback is. Springback means you deform a material, and when you release the stress, it springs back a little bit. And that's, of course, the elastic behavior, Hooke's law, but also the deviation from elastic behavior, and that's this anelastic behavior. So if we know the dislocation density, and the dislocation density depends on the local deformation, so it's not the same at all these points in a certain product, then we could use this concept, this knowledge on dislocation behavior, to predict springback better. And we did not manage to find a good equation for that yet. And I think the essential problem is there that in the loading curve, we describe an equilibrium situation. We have two stresses, they should be the same, and that gives in the end results in the equation that we use. In the unloading part, it's not an equilibrium situation. At the start that you start unloading, at the point that you start unloading, you have these rings outside the Frank-Reed source, but you have Frank-Reed sources that happen to be somewhere in their cycle of bowing out and coming back again. So the starting situation is not well defined, and we can therefore, we didn't come up with an idea yet on how to quantify this and really quantify springback and predict springback. Well, last few slides, a bit of history. This started 15 years ago already, when a master student presented her results on the plastic behavior. She studied the plastic behavior of a steel, and she made Cox-Makin plots, but she looked at the wrong part. So she looked at this part here, and she thought she was interpreting it, the plastic behavior, but the plastic behavior is here. But that's when we started to look at the extended Cox-Makin plots and to realize that there's information here as well. And that's also the reason why we look at the Cox-Makin plot and not at the tensile curve itself. It's sort of historically grown. But there is a problem with the Cox-Makin plot, is that you take the derivative. So to take the derivative, you get a lot more scatter than in your original measurements. So if you're scattering the original measurements, it's difficult to take the derivative. But recently we derived on the same basis equations also for the anelastic behavior. This should be no, this is the total strain. This is the anelastic part, and this is the lattice point. And see, we have again a certain equation in which everything is known except for rho and L. So we can also do the fit, and in this case it's the fit of the IF steel cycle 10. This is the tensile curve with the fitted curve, and we get the same values as for the Cox-Makin plot. So even if the measurements are not good enough to take the derivative, with this concept, it's also possible to do this fitting and get these parameters. Well, that's about it. That's the story of how to determine dislocation structure parameters from pre-yield measurements from the very first part of the tensile curve, and acknowledgement, of course, to PhD students, master students, technicians, colleagues that contribute to this. Thank you very much.
Thank you.
Thank you very much, Jilt.
Yeah.
We stop the recording.